Welcome to She's Mathy, a video series created to explain signal processing concepts in a visual way without using extended lines of equations and proofs. I'm Carolyn, and today we're starting a new series called Better Know a Theorem. The idea behind this series is that we, as humans, tend to grab onto certain details about famous theorems, and this is usually some rule that's been derived from the theorem, and we cling furiously to this rule without remembering its context, leading to a misapplication of the theorem. So these will be cautionary tales and reminders to take a step back and think through your application before applying constraints to it that it may not need. We are starting this series with my personal favorite example of this situation, sampling continuous signals. The fundamental theorem guiding most time series digital signal processing is, of course, Shannon's sampling theorem of 1949. But you should understand it better before throwing it at every sampling problem you see. Claude Shannon was a genius who worked for Bell Labs and is known as the father of information theory. His work catapulted us into the digital age. His theorem statement is very simple. If a function x of t contains no frequencies higher than b cycles per second, it is completely determined by giving its ordinates at a series of points spaced 1 over 2b seconds apart. The addition of Nyquist's name to the theorem has hazy origins, but he is generally credited with further stating the obvious implication of the theorem, which is that you have to sample at twice the highest frequency in a given signal if you wish to capture all of its frequency information. Thus, the Nyquist frequency is defined as half the minimum acceptable sampling rate and represents the highest frequency value that could or should be present in the signal that is being sampled. The Nyquist frequency concept is pounded into the heads of every student of linear systems or signal processing, and thus hordes of engineers are released into the wild, successfully trained to never, ever sample a signal at a rate slower than twice the Nyquist, and then all is well. But what does that mean, all is well? Let's discuss the implications of this theorem without using any equations to get an intuitive feel for what's going on. Most of you are likely familiar with the Nyquist frequency and why it is important, but let's start at the beginning for context. Let's say we take some samples of an unknown signal and plot them. It looks pretty obvious that the samples are from a sine wave that looks like this. But wait a minute, they could also be from a sine wave that looks like this. If we know nothing about the underlying signal and we sample at these points, we have no idea which of these two, or possibly infinite number of signals, is the true one. If it turns out that the real signal was the faster one, then we have lost the true frequency information from the actual signal and have mistaken it for a different one. This is known as aliasing. Say our faster signal has a spectrum that looks like this. It is a single frequency, and therefore, by definition, it is the highest frequency in the signal. Our sampling theorem tells us that we must sample at twice the highest frequency, which would be here. If we were to sample at a rate lower than that, say here, what would happen is that the spectrum would fold over the line that is half the sampling frequency. Now the signal represented by our samples looks like it is at the lower frequency, and we have lost half the information that the signal carried. We still have the amplitude, but we have lost the frequency information. That is because we violated the terms of the sampling theorem, and it serves us right. Given our samples, the only frequency we can infer is the lowest frequency that fits the samples. For all other sine waves that intersect these samples, we have no way of determining how many cycles they went through between each sample. We have lost their frequency information and have only magnitude information. Why would we care about that happening? Because proper sampling allowed us to transition from the analog age to the digital one, which massively reduced the amount of data that we need to keep in order to retain information. Since Shannon worked for Bell Labs, he was focused on communication. Sampling allowed information like sounds and images to be reduced in size via sampling, then transmitted efficiently across great distances and reconstructed back into their original form. You can do this because those samples carry everything you need to know about that information in order to reconstruct it. Think of sampling as a way of encoding a signal. Shannon has assured us that if we sample or encode our information correctly, then we have retained all the information necessary to decode it later. If someone sends you a bunch of sample values and tells you at what rate they were sampled, that's all you need to know. You can recreate the original analog signal without having any idea about what it was originally. This is obviously huge, and it's no wonder that when we start designing a system that involves sampling data, the very first thing that pops into all of our heads is speccing the A to D converter so that we can meet Nyquist. But here's where we need to pause and think about our application. Let's look at that theorem statement again and notice an important clause. quote, "It is completely determined by." For a pure sinusoid, the two parameters that completely define it are frequency and amplitude. But what if our application doesn't require being completely determined, and the processing we're going to do on our samples does not necessitate reconstructing the original signal? When we sample data and we automatically apply Nyquist, we may be overspecifying our systems because we didn't pay attention to all the wording in the original theorem. Clauses matter. For example, let's look at the process of measuring electrical power. This is necessary in more situations than you might initially think. Any control system that is in charge of energy delivery needs to track power. Electrical power in watts is defined as current times voltage. So to control power, you must measure your current and voltage signals, and this is often done digitally. If you are dealing with AC power, then those signals are sinusoids, and you might be tempted to dig into your toolbox of sampling knowledge and drag out Nyquist when choosing your codec. But let's back up for a sec before spending a lot of money. If you are dealing with AC power, then the measurement you really want is an average value over a certain interval of time. This is where a few equations are going to come in, but they are all basic algebra with a little bit of calculus, so stick with me. This is the calculation. Multiply your voltage and current signals together to get the power signal. Then integrate over some integer number of cycles. When we use samples of voltage and current for the calculation, the equation looks like this. Now, since we're dealing with AC power, we know that our underlying voltage and current signals are just sine waves of the same frequency, and it's reasonable to assume that their amplitudes are essentially constant over a small number of cycles. So really, we could write the power equation like this, where we move the independent variable to the sine function, and V and I are now just multipliers representing the amplitude of the sine waves. Next, we rearrange our terms like this. And further, we can pull the constant out of the summation and combine our two signs. Now, the most important step happens. When you integrate, or sum, sine squared over a full cycle, the answer is constant, 1/2. This shows that the average power has no dependency on the frequency of the voltage and current as long as they are the same. So, why would we need to preserve frequency when we're sampling? Remember the completely determined by clause in Shannon's theorem? In this case, we do not need our samples to preserve everything about the underlying signals. We just need it to capture the amplitude information, since the final calculation is just a weighted average of those values. So let's go back and look at the frequency domain. Sampling too slowly will alias the signal such that it looks like a sine wave of a lower frequency. But aliasing does not affect the amplitude of the signal, and that is the only piece of information we're interested in. We do not need a completely determining set of information. Still skeptical? Let's look at some examples in code. Take a nice innocent sine wave. There are about 14 samples per cycle in our demonstration here, so subsampling by anything more than 7 will produce aliasing. I ran some tests for both over and under sampling. The calculation used is to square the signal and to take an average over it, like our power calculation. If our previous discussion is true, we should see that the average of our samples of a squared sine is 1/2, no matter if those samples were aliasing, and we do see that. Want to make it harder? For good solid mathematical reasons beyond our scope right now, every signal possible in the universe is comprised of some sort of combination of sinusoids, even totally random signals. So let's try our theory on one of those. It's also beyond our scope here to derive what the mean square of a random signal should be. The important thing to notice is that I generated a random signal once, then downsampled it repeatedly, and the mean square remains the same no matter what. So the point of this presentation is to not follow rules blindly. You really need to understand the whys, the clauses of the theorems, and know when they apply and when they don't. You could be spending a lot of money on an expensive A to D chipset when you really don't need to. There are many more really interesting discussions that can spin off from this discussion. What are the effects of phase differences? Are random signals really made up of only sines? We'll get to all of these and more in the future. I'd like to thank 3B1B and the Summer of Math Exposition. Thanks for tuning in to She's Mathy.
And she's just my type!